Welcome to the solutions to the Regents Physics Springs and Simple Harmonic Motion problem set. Problem number 1. Let's go ahead and get started. As masses are hung from the spring shown at the right, it becomes more and more stretched out. The elongation of the spring, the total amount it has been stretched, is represented by X. The force producing the elongation is represented by F. The table below shows the elongation X produced by various forces F. A, on the axis above, graph the elongation of the spring as a result of the forces. All right, so we're asked to plot these data points, and when we go ahead and we do that, okay, we get a bunch of data points that look like this. And clearly, a linear relationship looks like is forming here. And so we go ahead and we draw a best fit line to our data. Looks like this one has a perfect correlation, passes through all the points. And there we go. We have a graph of elongation, and that's force versus elongation. Force on the y-axis and elongation on the x-axis. B asks us to predict from the graph the elongation produced by a force of 10 newtons. Pretty easy to do. Find 10 newtons, follow it over, follow it down. Looks to be halfway between 0.2 and 0.3. So we have an approximate answer here, 0.25 meters. C, the shape of the graph indicates what relationship between F and X. Well, clearly, because of the linear fit, it indicates that the force stretching the spring is directly proportional to the elongation. And the way to abbreviate that, force directly proportional to X. On a graph of quantities that are directly proportional, the proportionality constant comes from the slope of the graph. You've heard this several times already in the course. Calculate the slope of your graph. And what does this slope physically represent? All right, so to do this, we're going to want to pick two spots. Okay, I'm going to go ahead and pick, let's see here. Let's pick this spot right here. And let's pick this spot right here. Okay, and from those two spots, we're going to go ahead and calculate the slope of our graph. I'm going to pick two spots that intersect the grid pattern there. Slope is change in y over change in x. My change in y is 20 newtons minus 8 newtons. And my change in x is 0.5 meters minus 0.2 meters. I go ahead and I perform my calculation. It would be 12 newtons divided by 0.3 meters. And when I do the math, I get 40 newtons per meter. Now, this slope has a unit of newtons per meter. And this, of course, indicates to us that this is the little value, this is the lowercase letter k, and which physically represents the spring constant of the spring itself. The spring constant is the aspect of a spring which, no pun intended, remains constant as long as the integrity of the spring is not ruined. More to come on that in a moment. All right, E, using the appropriate symbols, show how one can go from saying two quantities are directly proportional to the same two quantities being equal to each other. Show all steps below. Well, there's two ways to do this. We can start off with Fs directly proportional to X, and then we recognize the only way to say that they're equal to each other is to multiply our X data, which in this case is the elongation, which coincidentally has the letter X as well, by multiplying our X data by the proportionality constant. Well, up here in D, we already found that the proportionality constant is the spring constant denoted by lowercase k. So by substituting k in, we can say Fs equals Kx. Another way to do this, and we've seen this before in the course as well, start off with the equation that represents the fit of our data, which in this case is a straight line. And that equation is y equals mx plus b. What data did we plot on the y-axis? We plotted the force stretching the spring. What data did we plot on the x-axis? We plotted the elongation of the spring, and that has the letter x. What was our slope? Our slope was the spring constant, lowercase k. And our y-intercept is, or is very nearly, 0. So our equation becomes Fs equals Kx. And this is what is known as Hooke's law. F, further masses are hung on the spring, and the results are shown in the data table below. All right, so we have two more stretches with forces added to the spring. And G says, plot these points on the graph. Do they continue in a straight line? All right, so what do we have here? We have 0.66 at 22 and 0.82 at 25. So 22 is 0.66, which is about right there. And at 25 newtons, which is halfway here, I believe it was 0.82. There's another data point there. Clearly, these 2 points do not fall on the best fit line, and you can see it's really tailing off in a different direction here. So no, they do not continue in a straight line. Why is this? What does this indicate about what happened to the spring? Well, what happened here was that the integrity of the spring was ruined, and technically speaking, that means the elastic limit of the spring was exceeded. If you ever had a toy slinky, a real one, a metal one, and your annoying little brother or sister played with it and stretched it out and ruined it, that's what they did to it, was they exceeded the elastic limit of your slinky. And so the spring constant is no longer constant. They've ruined the spring, and it's trash. It's no good anymore. All right, that'll do it for the answers to number 1 here. More on Hooke's law as we do and investigate number 2 in class tomorrow.